let's talk about how to do tsunami simulations using the open source software called funwave-tvd. This is actually a simulation that I just did for the 2018 Anak Krakatoa um, uh, volcanic eruption, which caused a big tsunami that killed like 430 people. So this is a simulation that's this is the color actually shows the surface elevation of the water wave um, about 6 minutes after the event, and then this shows the surface elevation, the water wave, at about half an hour after the volcanic eruption. So this results looks quite consistent with what people have already done previously using the same code, but with a different kind of approach for generating the source, right? So I'm going to talk about how I actually did my calculations. So let's start with um, the code. The code is called funwave-tvd, right? So this was um, based upon the original sequential funwave code, but it's changed its but it has changed the numerical method um, from purely finite difference to something that's kind of a more advanced, like close to a finite volume method or something. Um, and this kind of and this code actually solves uh, the Bosnesque model for water waves, right? So this is actually slightly more advanced than, it's maybe not slightly, but substantially more advanced than the shallow water, than the nonlinear shallow water wave equation. Um, because this Bosnesque model actually accounts for wave dispersion and also nonlinearity. So it's one step further, one substantial step further than the nonlinear um, shallow water equation. Nonlinear shallow water equation assumes that the wavelength is substantially longer than the uh, depth of the water, right? But in our case, the event was actually some kind of similar to a landslide, and the wavelength is not that long. Actually, it's different from those big tsunamis generated by tectonic earthquakes. Um, so this kind of a simulation actually requires you to actually consider wave dispersion, right? So you cannot just still use the nonlinear shallow water wave equation that's used for tsunamis generated by large tectonic earthquakes. You have to actually use a Bosnesque model that accounts for dispersion, for wave dispersion. So this website actually, this is the open source code, and this website actually gives you a quite detailed tutorial, right? What I'm gonna do is to actually uh, just document what I have done to actually set up the run on my environment, right? So what I did was to actually model downloading and setup, right? And then it's gonna take me to the uh, to the to the to location of to the location of the codes, the source codes. Um, yeah, so it's download source codes, right? But I did not use the version of beta, the latest test version, right? The version that I used was so if I click into it, it's yeah, it's gonna take you to um, do I have previous versions? Maybe I should click on the older versions, right? So maybe click on 3.4, right? And then it's gonna take me to all the stable versions. So the most stable, the latest stable version was version 3.6, right? So all I did was actually download this source code, right? I didn't actually use the beta, the test version. It's the stable version. It's the stable version. And then all I have to do is to actually transfer this code to my cluster and then try to compile it. So this is actually the on my local on my kind of on my on my class on the cluster that I have access to. This cluster is called the retro. It's a supercomputer in the Anchor, Wyoming Supercomputing Center. So I have access. So let's look at the setup of the code. It's so if I after I finish downloading it, I can actually put it in my home directory, and then this is called funwave-tvd. So I actually downloaded all the different versions, right? The one that I was actually using for simulations was 3.6, right? All I have to do is to just untar it and then unzip it and untar it, and then I can actually get the folder for the source code, right? If you look into the source code folder, you're gonna see a makefile, right? And this makefile is actually for generating a kind of a sort of a kind of a generating a binary, right? That doesn't have many of the kind of plugins or many of the individual capabilities. It's just a kind of a standalone kind of executable, right? So what I have to do, what I did was to actually create another directory called work, WRK, right? And then copy that makefile from the source directory into this particular directory. That's the same makefile, right? And then all I have to do is to actually edit this makefile a little bit, right? So I need to actually tell the make where my source code is located. It's going to be inside of this particular directory, right? And then what my compiler is, and my work directory, which is the current directory, right? And then my compiler, I want it to be parallel, right? And then the executable is going to be funwave, and then precision is double. So everything that I have to change is kind of limited to these first top few lines, right? And then after I make those changes, I don't really have to change anything else, and then I can just compile it, right? And then if I type make in this particular directory, it's going to actually create this particular binary executable, right? So if you want to create a debug version, sometimes you need the debug version to actually diagnose what kind of problem you may have, right? All you have to do is to actually go back to the makefile. There is a debug flag, right? So the debug flag by default it's going to be false, right? But if you want to change it to true, then it's going to compile a debug version with lots of a printout that allows you to actually diagnose what might be wrong. Um, and then this funwave-tvd actually has two different coordinate systems. One is the Cartesian coordinate system, which is used for a small region, right? Small region. If it's a simulation for a small region on the Earth, then you can approximate the Earth as a kind of flat, right? You can use a Cartesian coordinate system. But for the simulation that I was doing, I was actually using a spherical coordinate system. And if you want to use a spherical coordinate system, you have to actually set the spherical from false to true, right? So by default, it's going to be like a false, right? But what I have to do is to actually change it to true, and then it's going to compile a spherical version that allows me to do simulation for a large region. But the spherical version seems to have less capabilities, or less accurate, or less kind of amount of the dispersion, maybe weakly dispersed waves, right? So it's not like as capable as the Cartesian version. So once you actually have compiled this particular kind of base version, right? You can actually try to actually compile different kinds of executables with different plugins. So the next thing that I did was to actually, so if we look into this source directory, you're gonna see something that's a folder called simple cases, right? And this simple cases actually gives a very kind of complete documentation of previous simulations people have done using this code, right? So what I did was to actually copy this folder over into work, right? Then I have a simple cases, right? And then I can go in there and then try to actually find a directory or find an example that's closest to the simulation that I'm trying to do. And the one that I picked was Tohoku tsunami. That was the tsunami that actually caused the meltdown of the nuclear power plants in Japan, right? So that was like a big earthquake. It was a big tsunami generated by a huge tectonic earthquake, right? So if you go into that directory, you're gonna see something you're gonna see like 3 folders, right? External files, processing, and work. So if you go into work, you're gonna see another make file, right? And so if we look at this particular make file, you're gonna see that so this part is something that I have changed, right? These parts are what I have changed. And then the spherical setup is gonna be true, right? So all I have to do is to actually turn on this particular flag, and then it's gonna compile the spherical version, and I rename the executable to funwave spherical. Right? And then when I run this particular example, say I have a shell script here. If I do so that's sort of the shell script for running this particular example, right? What I have to do is to actually call this particular funwave underscore spherical, this particular executable that was created just underneath this particular example directory, right? And this executable was compiled using this particular makefile with the spherical option enabled, turns on true, right? And then all I have to do is to actually queue up run.sh to the cluster, and then it's going to run and produce the correct output. So if you run this particular executable, or if you run any executable of funwave, by default, it's going to try to actually read an input file that's called input.txt, this particular input file, right? And then if you actually look at its content, it actually tells you how to actually specify the different parameters that's going to be used by funwave, right? So what I did was for the Quercato volcanic eruption, what I did was to copy this particular input file and then make changes to those parameters that needs to be changed. So in particular, what you want to change is probably basically it requires four input files. The most important one is actually the bathymetry file, which is this file, right? And this file actually comes with the example itself. And then you're going to need some initial conditions. The initial conditions are specified in these files. So the initial condition is going to be the surface elevation, which is called eta, right? So the water wave is going to change the surface elevation of the ocean, right? So that's the surface elevation. Surface elevation file as used as the initial condition. 30 minutes is the resolution, the spatial resolution of the input file, right? So because it's in spherical coordinates, right? So the resolution is going to be in degrees, minutes, or seconds, right? So it's going to be, and then you're going to, so this is the surface elevation file. You're going to need 2 additional input files, initial condition input files. One is the u velocity, the other one is the v velocity. So velocity in this kind of Boussinesq model, you're going to actually reduce the 3-dimensional Euler's equation to 2-dimensional. So you're going to integrate over the vertical dimension. And then after you have integrated the vertical dimension for the Euler equation, the remaining part is actually a 2-dimensional problem, right? And then you have only x and y, 2 horizontal spatial coordinates, and then you also have your velocity. Your velocity vector is going to have like 2 components, 2 horizontal components, and the vertical component doesn't actually appear in the Boussinesq equation. So what you need is actually the 2 horizontal velocity in the initial conditions, and also it's 30 minutes, right? At this kind of same kind of spatial resolution as the bathymetry file. The bathymetry file is also 30 minutes. So basically, you're going to need these 4 different files as inputs to the codes, and then all the rest of the remaining parameters are going to be sort of adapted to the particular simulation that you want to do. So where are those files, right? These files are inside of the external files, right? So here you can see the 4 input files that's used, the bathymetry file, and then the initial conditions, the 3 initial conditions, right? And these files are all text files. They are not binary, so you can actually read them by using a text editor, right? So if we just look at the depth elevation, it's going to look like that. It's going to have a number of rows and a number of columns, right? We'll talk about the format in just a little bit, and the important thing is to actually make sure that the first of all, the dimensions of all the different files has to match. So these are the input files for this particular example case, right? So what I want to talk about is some of the pitfalls that I had. So if I go into the PRJ, go into my project directory, right, and funwave and Krakatoa, and then if I go into this spherical work directory, right, and then work, right. So this spherical subdirectory is sort of a more or less a duplicate of the Tohoku Tsunami subdirectory in the single cases subfolder, right? So pretty much the structure is kind of a duplicate, right? So you're going to see the makefile. The makefiles are also kind of similar, right? So if you look at the makefiles, it's the spherical is also enabled as true, right? One of the things that I found when compiling the code is that if I change the Intel compiler to GNU compiler, right? So suppose I change to GNU, and then in my environment I have to do a module swap Intel to GCC, right? So now if I check, it's a Fortune 90 code, right? So funwave-tvd is actually a Fortune 90 code. So if I check my MPI F90, it's going to show me that it's going to be a GNU version of the MPI F90, right? So now if I do my make, if I do make clean first, so it's going to delete all the make files, right? Delete and then do another make. So I'm gonna see something that seems to be puzzling to me. I wasn't able to actually solve the problem. It was seems to be related to the MPI. So if I right, so that's the error messages I got. So I wasn't able to actually compile the code. So basically, it was saying that this MPI R receive have a type that's a kind of a mismatch, right? So at position 1, it's expecting some kind of a integer, right? But at the position 2, it was expecting single precision real, right? And this kind of problem was just associated with the GNU compiler. If I switch to Intel compiler, I don't get the same kind of problem. So if I module swap GCC to Intel, right? And then if I do a make again, and this time the code is gonna compile, right? So that's one thing that I couldn't actually figure out. I actually spent some time to try to investigate that particular source code. That source code is actually, to me, it looks correct. ICN and I receive are called in the correct syntax. But I didn't actually see any kind of problem. The code, oh, I forgot to change the makefile. Right. It has to be in here. Right. So the source code that's associated with this particular problem is a, maybe I should switch to, so it's inside of this source directory, right? And then it is this particular source code, right? .picf, so parallel.picf, right? And then file exchange, right? That's this particular subroutine where you have to call this MPI I receive, MPI I send, right? But all the variables were actually defined locally, right? So it doesn't actually have any kind of a then these variables are not actually really reused until you go into these 5 variable names are not really reused until you go into a different subroutine, for example, right? And here you can sort of see it's real single precision, right? And then you have another subroutine that's called phi int exch, right? And then in this particular subroutine, all the variables with the same name are going to be changed to a different type, right? So, but all the variables are actually local, right? It's not actually some kind of global variable that you can actually have a mix-up with different types for different kind of calls, right? So I don't really see it as some kind of source code problem. The source code looks correct to me. Maybe there's some kind of problem with the MPI implementation, right? Or with the compiler. With the compiler that's actually specific to the machine that I'm using. So I don't really know. So for now, the Intel compiler seems to be working correctly without any kind of problem, right? So that's the only thing that I want to say about this compiling process. Once the compiling process is correct, the binary executable is supposed to be kind of usable, right? So it's so it should work, right? So it should work. So this is going to be the binary executable that I just created, right, with the Intel compiler on my machine, right? Yeah. So in the next section of videos, in the next group of videos, I'm going to talk about how to actually set up the input file and also the control file for running funwave-tvd, right? This particular input file, which is actually very important.